Machine learning technologies are a fast-growing area of artificial intelligence. These technologies have been used in many promising industry projects and scientific research, which has allowed machine learning to develop widely in recent years. Over the past decade, there have been a number of remarkable achievements in machine learning and in particular in deep learning. There are three factors that contributed to such significant progress in this area: mathematical theory that was already established before the current rising of machine learning and deep learning, development and improvement of quality and size of datasets, and last but not least, computing power that can handle these datasets has appeared. The widespread adoption of GPUs, virtual unlimited storage options, and the development of big data technologies have become the necessary basis for the evolution of deep learning. In this connection, the size and the complexity of neural networks are growing. More computing power is needed. Effectiveness and utilization of power of modern computers are one of the core challenges that machine learning and deep learning faces. Fortunately, machine learning and deep learning models have inherent parallelism. Exploiting and applying this parallelism to hardware is one of the most exciting and important research directions in modern deep learning. In this lecture, I will discuss the variety of topics in the context of parallelism and distribution in deep learning. We will not generalize this approach to machine learning, but focus on the deep learning itself. Especially, we are interested about neural networks. We will touch parallelism strategies for deep neural networks on different levels. You can see parallelism everywhere. Parallelism occurs whenever multiple agents work together in solving a larger problem. When one agent cannot solve the problem in time, this is where parallelism should be applied. You can apply parallelism for your computations by following simple algorithm. Take a larger computation problem, break it into smaller parts, solve the parts concurrently, and if necessary, communicate partial results, repeat until solution is reached. You are done. Parallelism can be everywhere in deep learning also. On every stage of deep learning pipeline, training taking majority of time and resources. Thus, we will focus on the training part in this lecture. We continue with a brief overview of parallel hardware architectures that are used to execute learning problems in practice. This system can be roughly classified into single machine, often shared memory, and multi-machine, often distributed memory. Parallelism is ever present in today's computer architecture. Internally, one on the chip, in form of pipelining and out-of-order execution, as well as exposed to the programmer in the form of multi-core or multi-socket systems. Multi-core systems have a long tradition and can be programmed with either multiple processes, multiple threads, or mix of both. Machine learning tasks are often compute-intensive, making them similar to traditional high-performance computing applications. GPUs and similar hardware like FPGA ASICs show the best results for both HPC applications and machine learning. Those devices focus on compute throughput by specializing their architecture to utilize the high data parallelism in HPC workloads. Generally, accelerated partitions of HPC clusters have divided by nodes, which contain several GPUs. However, even accelerated nodes are not sufficient for a modern larger computational workload. At the moment, distributed memory architectures with multi-nodes parallelism and accelerators, such as GPUs, have become the default option for machine learning at all scales today. Roughly speaking, parallelism in deep learning can be distinguished on a parallelism on three general levels. Concurrency in operators, which is parallelism on level of layers of neural networks. Concurrency in networks, that's a parallelism on the level of network itself. Concurrency in training, more general level, where multiple training agencies are communicate. During the training of neural network, we wish to minimize the generalization error defined by the loss function. Minimizing the loss function can be performed by using different approaches. Stochastic gradient descent is one of them. Stochastic gradient descent is an iterative method for optimizing loss function. In stochastic gradient descent, you calculate the gradient using just a random small part of the observations instead all of them. The gradients are calculated and the decision variables are updated iteratively with subsets of all observations, called mini-batches. Stochastic gradient descent can be executed concurrently through the use of mini-batches. However, setting the mini-batch size is a complex optimization space on its own merit, as it affects both statistical accuracy, generalization, and hardware efficiency, utilization of the model. Mini-batches should be not too small so as to harness inherent concurrency in evaluation out of loss function, nor should they be too large, as the quality of the results decays when increased beyond a certain point. In the most cases, computation, for example in the case of pooling operators, can be directly parallelized. However, computations have to be reshaped. Below, we list a concurrency analysis for two popular operators. First of them is a fully connected layer. A fully connected layer can be expressed and modeled as matrix-matrix multiplication of the weights and the neuron values. To that end, efficient linear algebra libraries, such as cuBLAS, which is an implementation of basis linear algebra subprograms up top on the NVIDIA CUDA runtime, can be used and can reshape and provide parallelization for these layers. Convolution contributes the majority of computations involved in training and interference of neural networks. While a convolution operator can be computed directly, it will not fully utilize the resources of many core architectures, such as GPUs, which are geared towards many parallel multiplication accumulation operations. It is possible, however, to increase the utilization by ordering operations to maximize data reuse, introducing data redundancy or via basis transformation. The first algorithmic change proposed for the convolution operators has the use of the well-known technique to transform a discrete convolution into matrix multiplication using Toeplitz matrices, also known as Im2Col. This method consists of reshaping the images in mini batches from 3D tensors to 2D matrices. A second method to compute convolutions is to make use of Fourier domain, in which convolution is defined as element-wise multiplication. In this method, both the data and the kernels are transformed using Fourier transformations, multiply, and the inverse Fourier transformation is applied on the result. Experimental results have shown that larger the convolution kernels are, the more beneficial this method becomes. The prevalent method used today to perform convolutions is Vinograd's algorithm for minimal filtering. Since the number of operations in Vinograd convolutions grows quadratically with filter size. The convolution is decomposed into sum of tiled small convolutions, and the method is strictly used for small kernels. Deep neural networks libraries, such as cuDNN, provide a variety of convolutional methods and data layouts. In order to assist users in a choice of algorithm, such libraries provide functions that choose the best performing algorithm given the tensor size and memory constraints. Internally, the libraries may run all methods and pick the fastest one. Another level of parallelism is a concurrency in networks. As most of the operators are independent with respect to data samples, a straightforward approach for parallelization is to partition the work of the mini-batch samplers among multiple computational resources, for example, cores or GPUs. This method dates back to the first particular implementations of artificial neural networks and has a name data parallelism. The second partitioning strategy for deep neural networks training is model parallelism, also known as a network parallelism. This strategy divides the work according to the neurons in each layer. In this case, the sample mini-batch is copied to all processes and different parts of the deep neural networks are computed on different processes which can converse memory, since the full network is not stored in one place, but incurs additional communication after every layer. Third approach combines both mentioned approaches. Pipelining can be viewed as a form of data parallelism, since elements, samples, are processed through the network in parallel, but also as model parallelism, since the neural network distributed to workers. A general pipeline parallel setup involves layers split across stages, with each stage potentially replicated and running data parallel. Multiple batches are injected into pipeline to keep it full in steady state. At the same time, in industry, the combination of multiple parallelism schemes are standard approach. The combination can overcome the drawbacks of each scheme. In distributed environments, there may be multiple instances of training agents running independently, and thus the overall algorithm has to be adapted. Directly dividing the computations among not only processors, GPUs, but nodes creates a distributed form of data parallelism, where all nodes have to communicate their updates to the others before fetching a mini-batch. To discuss and classify these approaches, we should consider model consistency, parameter distribution, and training distribution. First parameter that can be used for classification of neural networks is the presence or absence of parameter server. Thus, these neural networks architectures can be named as a centralized and decentralized. A centralized network architecture would typically include parameter server infrastructure, which may consist one or more specialized nodes, whereas a decentralized architectures would rely on all-reduce operation to communicate parameter updates among the nodes. Following communication, centralized parameter update is performed by the parameter server, whereas the centralized update is computed by each node separately. Every node creates its own optimizer. In decentralized training, the parameter server is omitted and instead has data shards to communicate updates to every other data shards in the network for each training example. The individual layer shards send their gradients to their parent data shard, which in turn sends a message to every other data shard informing it of a new parameter updates. While the all-reduce operation can be implemented efficiently for different message sizes and nodes, the parameter server scheme requires each training agent to send and receive information to or from the parameter server nodes. On the other hand, the parameter server can keep track of a global view of training, averaging the gradients at one location and enabling a synchronous operation of agent. Second parameter that can be used for classification of neural networks is a consistency. Before we discuss so-called only synchronous or consistent models, where updated weights are visible for every agent in a system. These kind of models have synchronization restrictions. Recent works relax these synchronization restrictions, creating asynchronous, inconsistent models. Asynchrony can be implemented for both centralized and decentralized models. A well-known instance of inconsistent architecture with parameter server is a hog-width algorithm, which allows training agents to read parameters and update gradients at will, overwriting existing progress. To guarantee correctness in spite of asynchrony, stale synchronous parallelism can be implemented. This approach proposed a compromise between consistent and inconsistent models. The gradient staleness is enforced to be bounded by the performing a global synchronization step after a maximal staleness may have been reached by one of the nodes. This approach works especially well in heterogeneous environments. Moreover, it is impossible to talk about parallel and distributed deep learning and not talk about optimization. Training of a deep learning model can be described as a nonlinear optimization problem. Furthermore, it is possible to use computational power to perform meta-optimization. or searching for better hyperparameters and deep neural network architectures. In this lecture, we will touch on the hyperparameter optimization. The multitude of hyperparameters in neural network model, for example, learning rate, momentum, maximum stillness, and their adverse effect on the resulting accuracy, hinders research efforts into new techniques and machine learning. Until recently, the prominent method for the hyperparameter search was to perform parameter sweeps, like a grid search. Since the method increases the overall time exponentially with the number of hyperparameters, its effectiveness is limited by the availability of computing power. However, there is a new generation of hyperparameter optimizers who can suggest a solution for this problem. One of them is OmniOpt, a tool for hyperparameter optimization on HPC. Lecture about it you can watch on our channel. In this lecture, we try to cover the most important areas and directions in modern parallel and distributed deep learning. In the end, I would like to summarize my talk with a few points. First, nearly every aspect of training, from the computation of convolution to the meta-optimization of deep neural networks, is inherently parallel. Networks of all sizes, from billion parameter size models to tiny models, are parallel on every level and can be distributed. Nowadays, deep neural network architectures are becoming deeper and more interconnected. Computing individual operators are highly optimized today. In this context, an important and one of the most interesting areas of deep learning research is interlayer and whole deep neural network optimization. Thank you for viewing this lecture. See you in Levin Lab.